one dealing with the Zoom interface here, as previous speakers have very cleverly done. If you want to keep the little video screen up, you can place it in the lower right and you won't miss anything important. And then as I was kind of testing out this interface, I noticed there's a little bit of a lag as I changed slides of a few seconds. And so I have the chat box up for myself. So if it seems like I've skipped a slide or I'm not talking about what's being seen, I think if you just leave a little note in the chat being like, I don't see what you're talking about, let me know, and there might just be a lag and it can catch up. Yeah, little logistics out of the way. I can just dive in here. So I'll be talking about mapping and classification of volcanic deposits using multi-sensor unoccupied aerial systems. And this is work I primarily did at my previous postdoc at Lamont Doherty Earth Observatory, which was funded by a NSF postdoc fellowship, and I was working there with Not Lev. As Joe mentioned, I'm currently a postdoc at the Hawaiian Volcano Observatory, but this talk will be primarily work I've done previously at Lamont. And before leaving the title slide, I'll just acknowledge all of the other co-authors on this work at a variety of different organizations, as well, including especially the help from Instituto Geofísico in Ecuador, who helped arrange the field visit for this study. So, excuse me. First off, just kind of start off with the understanding that we have that identifying and mapping the deposits from volcanic eruptions is essential for understanding eruptive processes, but as I think many of us are familiar with, there we go, there's the slide change. Many of us are familiar with, volcanoes can be very difficult places to do field work, and that can be due to both extensive deposits, extensive flow fields that are very difficult to traverse and map on foot, and also having to deal with ongoing activity, as seen in this photo of Fuego in Guatemala, can have ongoing activity creating hazards, and also just very steep and unstable edifices to work with. And so for these reasons, for a number of years, remote sensing applications from a variety of platforms have been very useful for the mapping of volcanic deposits, in addition to a number of other applications to volcanic systems. But for this talk, I'll be talking about kind of mapping and identification of, talking in the context of mapping and identifying volcanic deposits remotely. And so looking at satellite remote sensing, just from visual wavelengths, visual bands, we have this example from a paper on the 2010 eruption of Merapi volcano in Indonesia, using high resolution visual images to look at before and after effects of pyroclastic flows, and identifying features of these deposits on the scale of meters, and this is from just high resolution visual satellite images. And then also on the right here, we have a study from Lee et al. From a few years ago, using Landsat, multiple bands from Landsat satellite images of Nyamiragira in Africa, to identify and classify lava flows from different eruptive periods in the volcano's recent history. That's just visual. Looking at thermal remote sensing, very useful both from just the aspect of identifying volcanic hotspots. On the left is a series of images from the Astra satellite showing the 2006 eruption of Merapi. And then thermal, in addition to showing hotspots from active emplacement of eruptive material, for cooled deposits, you can actually use thermal data to analyze the physical properties of the deposit. And so Mike Ramsey at University of Pittsburgh has done a lot of work in this vein. And so on the right is an image where from a study of his, where he used the multiple bands and the thermal wavelengths of aster to get at the vesicularity of material in a pyroclastic flow deposit of Shiveluch. So that's one of the things you can, in addition to thermal radiance and hotspots, you can actually get at some of these physical properties of deposits with the thermal bands. As you know, any data type, there are trade-offs exist for any type of remote sensing platform, and so I'll kind of be talking about this in the context of satellite versus drones, because each have their advantages and disadvantages. And so first, with satellite, you generally have a big trade-off between your temporal and spatial resolution. And so the more frequently you have images, the lower the resolution is. And this, for visual images, this is becoming less true, in that with the number of visual satellites that are orbiting Earth right now, and the number including CubeSats and different platforms, we're almost pretty much to the point where you can get meter scale or sub-meter scale imagery almost any day. But this resolution trade-off is still very true for satellite thermal imagery, and this is shown kind of in the top right here for looking at the Merapi eruption in 2006, whereas for the visual image, you have meter resolution that you could get at that time every few days. If you wanted thermal data, you were looking at Landsat, which is a 30 meter thermal pixel. In this case, I'm showing an aster pixel, which is 90 meters, and at best case scenario, you're looking at getting an aster image about every week. Sometimes it's the repeat interval is 2 weeks to get a 90 meter pixel. And even going from 1 meter to 90 meter, you have a massive reduction in the detail, the spatial resolution and the detail that you can see. And if you're looking for a daily thermal image, you're looking at MODIS, which you can get multiple images a day, but you're looking at 1 kilometer resolution. So that same eruption, which in visual, you can see an actual actively moving pyroclastic flow in the visual image. In the thermal image, it's basically a slightly brighter blur if you want a daily image. And then in addition to this contrast in spatial and temporal resolution and resolution between visual and thermal images, you can have atmospheric interference, both from the volcanic eruption itself, seen in the plume from the pyroclastic flow in the visual image, and also you can just have atmospheric clouds interfering with data collection. So this example in the bottom of the slide is a DEM that Nakata et al., paper from a couple years ago, made using 2 high-resolution visual images. And so this is a DEM resolution of a couple meters that works pretty well for looking at the Cinnabon lava flow, but then because of the clouds that are present in one of the visual images used to make that DEM, these clouds prevented this DEM from being able to resolve the vent area, which can be very important. Volcanoes are often cloud covered, and so it can be rare in a lot of cases to get a clear satellite image of the vent area of a volcano. And so then comparing that to drones, using drones, what you're going to sacrifice basically what I called spatial coverage and data access. And so with satellites, you can image large areas, whereas drones are limited in spatial coverage because they have, they're ground, you have to take off from the ground. They only have certain battery life. et cetera. And then many satellite images, anyone can go onto websites hosted by NASA and other organizations and download the satellite data many times, quite frequently for free. And so there's advantages to spatial coverage and data access for satellite data. But if you are in a case where you're willing to kind of sacrifice that for drones, and you're able to use a drone in the field yourself, you gain user control of the spatial coverage, the area that you're mapping, the resolution that you're collecting the data at, how frequently you're collecting the data, and what type of data you are collecting. So you gain control of all these things. And so drones are most commonly fitted with visual cameras, but they can also carry thermal cameras, which I'll talk a lot about in the following slides. And then many other, and then other people for volcanic applications are putting gas sensors, devices that can sample plumes, and also geophysical equipment. So you get a lot of flexibility in terms of what type of data you collect using drones. And so this kind of being able to define your own resolution and mapping context is a big advantage of using drones for studying volcanic systems and volcanic areas and volcanic deposits. In addition to the fact that drones are becoming a lot more affordable and easier to use and accessible. So those are kind of the two big components of why drones have become so popular in volcanology in the last few years. And so the examples on this slide are showing different ways to use just the visual data, the visual images that are collected by drones. And so the most common thing to do with the visual images, in addition to just using them to monitor and look at the terrain from unique perspectives, is you can use photogrammetry to create visual orthophotos and digital elevation models of areas, and then you can repeat these surveys, and so you can get repeat DEMs and look at volume change. And so the examples on the left are showing dome growth at Colima in Mexico, and then also lava flow, the placement of the lava flow and pyroclastic flows at Sinabung. And this image in the middle is using just the visual orthophoto from a drone flight and photogrammetry just to map structures in the lava dome at Merapi. And then from using a thermal camera mounted on a drone, you can you can make just temperature maps. So on the left here is a temperature map of Lucy Mud Volcano showing the vent and outflow channels. And then thermal images can also be really useful for looking through diffuse plumes that are very commonly present at persistently active or actively degassing volcanoes. And so this example in the middle of the slide is showing how in the thermal orthophoto, not using temperature, just using the pixel brightness, it's a lot easier to identify all of the different vents. This is at Stromboli. You can see the vents in the thermal orthophoto, and you can actually see bomb fields from some of the Strombolian explosions. You can see these features a lot easier in the thermal orthophoto compared to the visual orthophoto. In the visual, you can see little incandescence. You can see one of the vents here, but some of the other features in the recently in place bombs are obscured from the gas plume present. So thermal imagery from drones can be really useful in that context as well. So the goal of this particular study is kind of to leverage the drone's ability to collect multiple data types and use that to map volcanic deposits. And so what we do here is use the visual camera and the thermal camera on a drone to create maps that look at different types of characteristics of the surfaces and use these different characteristics to map the deposits. And so instead of some previous mapping exercises or classification exercises or classification studies that looked primarily at just a visual orthophoto or just a DEM, we're looking at data collected from both a visual camera and a thermal camera, which emphasize different characteristics of the deposit. And so in addition to using these multiple data types, then we're also testing various classification methods by applying a simple manual and also machine learning techniques. And so the drone that we used in this study is the DJI Matrice 210, which has this capability to have two different cameras mounted to it at the same time. And so we have it with a visual camera and a thermal camera, and this allows us to collect our data simultaneously. The study area that we went to was the deposits from the eruption of Sierra Negra volcano, which is on Isla Isabela in the Galapagos archipelago. It erupted on June 26th in 2018. And this eruption started with lava coming out from multiple fissures at the same time, as you can see in this great image on the top right here. You can see multiple fissures active simultaneously, multiple lava flows. This widespread activity was only lasted for about a day, after which, basically starting June 27th, all activity focused in the Fissure 4 area, and that area was active for about 2 months before the eruption ended in August of 2018. And then we did our field work in October of 2018, so a few months later. The specific study area and all the maps I'll be showing from here out are just this tiny little area up near the far southeast part of Fissure 1, which the arrows are pointing to the vent areas where we focused on. And so the drone survey design is shown here. We did 3 flights on October 22nd. Each flight was approximately 75 minutes apart. Each flight lasted about 24 minutes, produced about, we were able to get 450 images from each camera, and we flew at about 150 meters above ground level in this, standard kind of mapping pattern. And all the maps from here out are going to be focusing on this this yellow box. So we took the images and applied the structure for motion photogrammetry technique and did all the processing in the Agisoft Metashape Pro software package. And that gave us data with about 20 centimeter resolution, both in the visual and DEM and thermal data. And so looking at the visual image data products, first on the left, we have the visual orthophoto showing the study area. And so just to kind of describe what we're seeing here is the vent areas are located kind of here in the south, or the southwest, or the lower, kind of the lower left side of the visual orthophoto. These are the vents. The flows then proceed north and east. Most of the upper part of the flow here and here are Pohohoi lava, both with large portions of intact crust and also kind of slabby Pohohoi type, where the crust starts breaking up as it flows down slope. Then as the flow goes north, it transitions to an lava type, both flow branches. So in the north part of the flow, it's and then the rest of the terrain, you can see the primary ground cover is just tephra or scoria, with outcroppings of craters and cliffs and lava flows from older eruptions. The DEM, 20 centimeter DEM that we produced is located in the center. And from the DEM, we calculated the slope of this ground surface at every pixel. And we use that slope map to calculate the surface roughness of this area. And so there's a lot of different ways to calculate the roughness of a surface. In this case, kind of for computational simplicity, we calculated the roughness as the standard deviation of the slope in a moving 5 by 5 pixel window over the whole map. And so a 5 by 5 pixel window is about a 1 square meter area. So this is going to be sensitive to changes in the surface texture on the order of 1 meter. And of course, you know, the relative roughness of a surface is going to be sensitive to the scale at which you calculate your roughness. And so you want to, you know, so something that's really rough at the order of 1 meter could appear very smooth if you're doing your, you know, if you choose a scale of 10 meters. And so when working with roughness, you want to make sure it's sensitive to the scale of feature that you're interested in. In this case, the sections of the hoi hoi crust and the blocks that we saw and the features in the flow are all on the scale of, you know, a few tens of centimeters to meters. And so we figured, you know, we kind of 1 meter is a good roughness scale in this context to look at, to look at the different features in the lava flow. And so that's what we did, or actually, and then actually looking at the roughness map itself, just a few things to point out. You can see that tephra is the smoothest surface. Tephra area is very smooth. The lava is in general rougher than the tephra. The pahoehoe sections kind of have both relatively smooth and relatively rough segments. The is kind of hard to see, but the is kind of a little more uniform and kind of intermediate roughness values compared to kind of the in-member pahoehoe roughness values. And so that's one component of the data we're using to classify that we derive from the visual images. And so then looking at the thermal images, this is why we flew 3 flights. And so we were able to create a time series of temperature maps of the area. And we can see in the earliest flight with the lowest, the least, you know, so the surface is heated the least due to solar input at this point, because still early in the morning. Most of the surface temperature is roughly the same, and there's some hot spots that you can see due to the flow, which was about 4 months old at this point, still cooling in places. And so, but what we're most interested in for this is actually the places that are already cooled, unaffected by the flow and placement, or that have already cooled fully from being in place. And so as the day goes on and the ground surface heats up because it was a sunny day, we can actually see different portions of the surface heating at different rates. And so you can see the tephra surfaces are brighter in this last image compared to the which is darker or cooler. And so we can see different types of volcanic deposits are heating at different rates. And this is due to a physical material property called thermal inertia. And thermal inertia is basically a material's ability to resist heating due to external forcing. And so in this case, this is solar heating, and the higher thermal inertia the material has, the more it's able to absorb the solar input, and the surface of that material is going to appear to heat slower because the material needs to absorb more heat before its surface heats up. And so the thermal inertia is calculated as the square root of the thermal conductivity, the density, and the specific heat. And so you can see, so it's sensitive to density. And so if you look at the equation, as the density increases, the thermal inertia is going to increase. And so denser materials require more solar input to heat up compared to less dense materials. And what this will be relevant for in the study area that I'm talking about today is vesicularity. And so less vesicular lava is going to have a higher thermal inertia than highly vesicular lava, which will have a lower thermal inertia. Thermal inertia is also sensitive to particle size, just in the sense that a big block of something is going to be able to absorb more heat and conduct that heat into the subsurface compared to a smaller particle. And so one kind of example to kind of thought experiment is if you imagine standing in bare feet on a sandy beach on a hot sunny day, the surface of the sand is going to be very, very hot because the sand is very small particles, and it can't conduct the heat from the sun. It can't conduct that efficiently into the subsurface, so the surface of the sand gets very hot. But then if you're standing there and you dig your feet a few inches down into the sand, it's a lot cooler because the heat can't conduct down in there. And so that's kind of a little thought example of how the thermal inertia works in terms of particle size. Another example in terms of like the same beach, if you're on the sand and there's a large boulder, if you jump from the sand onto the boulder might actually be cooler and you're able to stand on that more because it's absorbing the heat as opposed to radiating it back out. And so this is a physical property that can be really useful in a lot of contexts, and it's used very commonly actually in planetary science and on Mars to look at where the relative abundance of bedrock exposures compared to dust-mantled surfaces. And then on Earth, it can be used in a similar context. And so the image on this slide is again from some of Mike Ramsey and colleagues' work using aster data to calculate an apparent thermal inertia of a rhyolite flow in the Mono Lakes area of California. And you can see the high thermal inertia values are associated with places along like the north ridge of this flow where blocks of the rhyolite lava are outcropping along the crest of the margin of the flow, and you have lower thermal inertia values in the middle of the flow where it's mantled by tephra and other deposits. And so what we do with the drone data is actually use the time series of temperature maps to calculate the solar heating rate. And so solar heating rate is a proxy for thermal inertia and varies as the inverse of thermal inertia. So a high solar heating rate is comparable to a low thermal inertia material. And again, this is sensitive. This is going to be this data type is going to be sensitive to particle size and density of the material on the surface. And so in this heating rate map of this area of the lava flows, the tephra, which has the smaller particles, have the highest heating rate. The lava is slower, but we can see that the lowest heating rates are associated with the A'a lava, and the Pohoihoi is kind of intermediate. You can also look, if you follow the purple lines down flow, you can kind of see a trend of the heating rate decreasing as you move down flow, and that is most likely associated with the degassing of the flow and becoming less vesicular and more dense as you move down flow. And so as you decrease the vesicularity, increase the density, you're increasing the thermal inertia, you're decreasing the heating rate. And so this is the other data type that we use for the classification. And so we have roughness, which is kind of sensitive to surface morphology and topography of the flows of the volcanic deposits. And we have the heating rate, which is going to be sensitive to kind of the physical properties, the density or the particle size of these deposits. And so to classify them, we applied a few different techniques and a couple different types of classifications. We had kind of a general classification, which I've kind of already talked about in the sense that we have tephra, A'a lava, and Pohoihoi lava over this area. And so then we also did a refined classification with 5 categories where we kept tephra as its own category and split the 2 lava types into subtypes. And so these are Pohoihoi with intact crust, which looks like this image in the center. And this is mostly located kind of on the margins of the Pohoihoi part of the flow and also near the vent. We also have slabby Pohoihoi, which is located a little bit more downflow, kind of in the channel where the intact crust was becoming highly fractured as the lava moved down away from the vent. And then in the A'a, we have blocky A'as, where you have primarily in the main channel, where you have a wide variety of just randomized block sizes in the lava. And then we also have what we call ridged AA, which is located primarily kind of on these, excuse me, this ridged AA is kind of located primarily on these short-lived flow lobes. You can see they have more uniform block size on the surface, and you kind of see these ridge-like, pressure ridge-like features on the surface. And so just from mapping and kind of visual inspection in the field and looking at the drone images, these are the kind of the categories that we chose to classify this area by. And so for the manual classification, this is what all of these numbered boxes are that have been in these figures, is we took the average roughness and heating rate from each one of these 31 boxes and plotted them in what is effectively a regime diagram. And so the colors represent the different categories, and the thick lines are the 3-category boundary, and the 2 thin lines are then the lava subtype boundaries. And so this is the manual classification. We just drew these straight lines to kind of divide up the different surface types. It's not a perfect classification. You can see especially one outlier in this region 29, but you can kind of see the same patterns I discussed in the map images, where we have AA with a slower heating rate than Pohohoi, Tephra with the highest heating rates. Roughness is generally, there's no clear distinction in roughness between the 2 main types of lava, but if you look at the roughness comparison between like the slabby and intact crust subtypes of Pohohoi, there's a clear distinction in the roughness. And so these are kind of the distinctions that we're getting at in this classification. And so this was how we defined the manual classification. These regions were also used as the training data set for the supervised machine learning, where we used a random forest algorithm. And so basically what that does is this random forest algorithm uses these region average values and kind of, and just assigns classification to every pixel based on their similarity to kind of clusters defined by these different areas. And so this image is the manual classifications lines removed. And in this case, the supervised machine learning just classifies based on similarities to these different clusters that are defined by our training data. And then we also applied an unsupervised machine learning k-means algorithm. And so unsupervised means there's no previous knowledge or ground truth information needed. There's no training data. The only thing we defined in this case was the number of categories to use in the classification, so that we could match the categories that we chose in the manual and supervised techniques. And so the unsupervised, we just tell it, okay, split it into 3 categories, split it into 5 categories, and then the algorithm groups the data based on similar characteristics that it sees in the data to that same number of categories. And so looking at the classification results, on the left, the big map is the 3-category manual classification. And so comparing to the ground truth that I explained a few slides ago, you can again see it does identify the tephra areas pretty well. We have Pohohoi located near the vents, and then transitioning to AA lava downflow. And the AA lava is very well identified, very little misclassification in that area. There's a lot of red, there's a lot of Pohohoi identified pixels in the tephra, and that's not necessarily misclassification. It's basically identifying areas where the lava and deposits from previous eruptions, craters, bedrock exposures exist. It's where those features exist, and they haven't been mantled by tephra deposits yet. And so one thing is with this data is that there's no distinction between the deposits from 2018 and deposits from a few decades ago. And so older lava also gets classified as, you can see in this region 7 here, where this is an older an flow from a previous eruption. The supervised machine learning classification, because it was trained on the data from the manual classification, very nearly identically reproduces the manual classification. Does a pretty good job of identifying the same stuff that we saw with our own eyes. The unsupervised machine learning deviates a decent bit in the fact that the Pohohoi class category basically disappears. And so what the unsupervised machine learning technique saw was basically the distinction between the tephra in the green and the lava flow, which is in the blue. It didn't see Pohohoi as a third significant cohesive mappable unit. And so in the unsupervised classification, the third category ends up being basically edges. And so you can see the red showing up along channel margins, levees in the flow, and along the edges of blocks of Pohohoi crust in the flow. And so that's what that method thought was the third most identifiable category. So moving on to the 5 category classification, there's more categories, so it's going to look a little noisier. To look at here is it's not, because the resolution of the classification is 20 centimeters, the 5 categories isn't good at, and it's a per pixel classification, so it's not grouping similar, it's not grouping the majority of the pixels into one visible cohesive unit. It's actually, identifying in the slabby Pohohoi area, it's kind of identifying the areas of the edges of the fractured blocks, and actually the red here, like the surfaces of the slabs of Pohohoi crust. And so the resolution is actually high enough in this case to identify it that instead of showing one cohesive unit of intact crust Pohohoi versus slabby Pohohoi. And in the case of some of the intact crust, we actually have tephra mantled surfaces here showing up as tephra, and in some parts the crust is so smooth and heated up so fast, it actually gets misclassified as tephra. And then the kind of a similar problem. We do have more dark blocky type here and more ridge type here, but in some cases you're actually identifying the differences between individual blocks and the surrounding area of the flow, or individual ridge forms. So again, this is kind of a discussion in terms of the scale or the resolution that you want to be doing this classification at in order to produce kind of what, are the most visually appealing or result. Supervised machine learning, again, does a pretty good job. There's some more misclassification in the tephra areas compared to the manual classification. And then the unsupervised machine learning, again, deviates kind of significantly from the manual and supervised in that it splits, instead of splitting the Pohohoi into multiple categories, it splits the tephra into 2 different categories in green and red here. And this is kind of based on whether the slope of the terrain in the deposit area, and also whether or not this deposit was like sun facing or not sun facing, so how quickly it heated up. And so it divides the tephra into 2 regions. It keeps the as one solid unit of lava, and then in the Pohohoi area is kind of a mix of everything. It actually this classification does kind of identify a lot of the slabby Pohohoi type where it appears. And then the light blue category ends up being edges again. So it's hard to see in this image depending on your resolution of all your screens, but the light blue kind of shows up mostly along channel margins. In here, there's a lot of light blue, and then also along levees in the flow. So again, the unsupervised technique is kind of identifying different major units than what we identified manually. And so those are all the different classifications. And so kind of the main big takeaways. First is that the solar heating rate that can be derived from drone data can identify changes in the physical properties of surface deposits. A couple important notes related to this is it's not restricted to just volcanic deposits. You can apply you can do the drone flights and measure solar heating rate of any type of deposit to look at differences in particle size and density of the deposit. And it'll also be sensitive to water content. Water will increase the thermal inertia, decrease the solar heating rate of a material. So it's broadly applicable. And also then it gives you kind of a comparable data type to thermal inertia data that's collected in planetary science, primarily for Martian surfaces. And so there's potential for planetary analog surface comparisons with the solar heating rate data. The solar heating rate is also going to be more sensitive to changes in particle size compared to topography-derived roughness data. And so you can see subpixel variations in particle size, whereas with solar heating rate, whereas for DEMs or roughness derived from DEMs and visual data, you're really you can only measure particle size variations or measure block sizes on the scale of the resolution of your data, of your pixel size. Additionally, combining the solar heating rate and the roughness together improves the identification and characterization of the deposits by including both physical characteristics from the thermal data and morphological characteristics from the topography from the roughness data. And then each classification we applied has its own strengths. The manual method we applied was very simple and straightforward. 2 components, we drew straight lines, nice and quick. And you don't have to, have an understanding of machine learning to do it. For the supervised random forest algorithm machine learning, it's based in the ground truth, and so you can have a targeted study. If you want to be able to identify different lava morphologies, you can train the algorithm to identify those morphologies and create a classification based on that. And then it's also then a lot more expandable than the manual method in that it's a lot easier for the computer to deal with additional categories or additional data types compared to the manual methods. So this is kind of a future work thing, but for the machine learning techniques, we can include additional data types beyond roughness and heating rate to include in the classification identification of units. So we can include things like the visual data, the visual orthophoto. If we wanted, we could do roughness at 1 meter scale and roughness at 10 meter scale if we wanted to kind of try and capture more nuance in the classification. And then for the unsupervised method, there's no ground truth needed. So if you don't have the ability to ground truth, you can still go out and map, and the unsupervised machine learning algorithm can identify the major units, which you can then visually inspect through the drone images later and kind of figure out what the major units in the mappable area is, which can also be useful for various applications. And similar to the supervised method, it's expandable to multiple data types and categories. And so with that, I will take any questions. Thanks for listening a little bit beyond the 30-minute time scale. So thank you.
Thanks, Brett. That was excellent. And I'll open this up for questions. Looks like we have a question in the chat to get us started here. The question is, why were you not able to drive thermal inertia? And what additional data would you need to do it?
So thermal inertia, or any type of thermal remotely sensed data is very sensitive to atmospheric interference. And so to derive a quantitative thermal inertia value, you need a detailed atmospheric model. And that wasn't possible in this context, and we didn't have the equipment with us to measure the atmospheric humidity in our immediate field area to do the atmospheric correction with the drone data. And it's actually really hard to do thermal inertia at all on Earth at all with any type of equipment. And so even the ASTER data, it's an apparent thermal inertia rather than an actual quantitative thermal inertia. Thermal inertia is really useful on Mars, and the fact that the atmosphere is much thinner there, and it's kind of simple enough to model accurately. And so thermal inertia as a quantitative value is primarily only used on Martian surfaces, and on Earth it's an apparent thermal inertia. And in our case, we just use heating rate because it avoided the complications of atmospheric corrections. And while we can't be too quantitative about the variations that we're seeing in the heating rate, it does show qualitatively, relatively, it does just as good a job as a quantitative value in terms of identifying the different deposits. So yeah, that's a long answer to that question, but the heating rate does just, does a really good job of showing the relative differences, which is what we were interested in this study.
Right, and as you were talking, there's a follow-up there, and I think you answered it while you were talking though. But if you have further questions for Brett on that topic, let me know. But I think basically the follow-up was, have you tried classification on pixel clusters? Are they more or less successful?
Mm-hmm. And then I see the next question I don't quite know what's meant by pixel clusters, but then I see the next question also being coarser resolution. And so I'll maybe kind of answer those together, because I have my first backup slide addresses that. And so this is a really basic resampling of just the classification. And so on the left is just resampling the classification from 20 centimeter resolution to 2 meter resolution, basically on taking just the majority classification within the resampling window. And so this does kind of have that result of kind of seeing more cohesive units like you do with your eye. You can look at the drone image, you can look at it in the field and see, you can see, oh, that's a region of slabby Pahoehoe. That's a big region of intact crust. And when you resample the classification, you do start seeing, you can see, okay, here's all this slabby Pahoehoe. And then you can see, okay, here's a lot more, here's a region of ridged here's a region of blocky So yeah, when you resample to different resolutions, you do kind of see an improved cohesiveness of the different units. Of course, you kind of have to pick the right resampling, because if on the right here, this is 20 meters, and in this point, it's starting to look a little more, it's starting to look a little more scattered. So it's kind of, you have to like pick, you have to keep resampling until you see the result you want. And one thing I'll try with this in the future is resampling the input data itself. So when, kind of a future work thing is resample the heating rate itself and resample the resolution itself and redo the classification, and see how that works. There's a lot of massaging or manipulation of the data that you can do to kind of vary this. And in this particular paper, this talk, there's only time to include so much.
Is there much value in doing repeat thermal IR measurements? Can you start to tease out some of the competing effects that lead to the inertia?
Yeah, so that would be interesting. So one thing that we can't do with this data is kind of look at the relative effects of particle size versus density. And so I can't say that the downflow trend is entirely due to an increase in density, just the same as I can't say it's entirely due to the block size of the AVA increasing. And so being able to dive into that would require a little bit more sampling and of actually field sampling and ground truthing. I haven't thought about kind of repeating the time series of flights on multiple days to see if things vary. That would be an interesting thing to do.
Thanks. Then we have a couple more questions, I think, in the chat here. So Stefan writes, as you mentioned, the slope with respect to the incoming sun has a large effect on the heating rate. That is, comparing control areas 2 and 3. Seeing as you have slope data for all these areas, could you feed that to the machine learning approach to tease out a sunshine slope correction for the heating rate, or manually get at that by plotting heat rate versus slope?
So short answer is yes. We haven't done it yet. What was kind of the simple correction in this talk is you can see in the heating rate map and actually all the classification maps, below the data, the base map is a hill shade of the DEM. And so the reason why there's no data in those places, you can see through the heating rate to the hillshade surface, is to account for solar effects. In this study, we just eliminated every pixel that had a slope greater than 20 degrees. And so we just masked out all the steep surfaces to account for the slope effects on solar heating. But that is, again, another future work of actually trying to calibrate, trying to include steeper surfaces and then calibrate it for the slope influences. And also one way to do that is there's also Aster has a derived reflectance product, and so you can actually, that's already calculated at a 90 meter pixel size, and so that's something we're also looking at applying is doing a reflectance correction. So we haven't done that yet, but we're aware of it. And so there's a future proposal on all this that will involve a very detailed calibration, ground truthing drone study. And in this particular case, it was kind of we kind of thought of the idea while we were already there to test it out. And so there's a lot of, if it was fieldwork specifically planned for this specific experiment, we would have brought some additional equipment and done a few things differently. And so in the future, we'll be doing some more calibration with this technique for sure.
Thanks. Okay, we have a few more questions in the chat. Ben writes, have you considered validating the supervised learning classification by 1, training the algorithm with one area, and then 2, classifying a new area with that data set and validating it manually and independently classifying the same area?
Yeah, have thought about it. Future work bullet point. Haven't done that part yet. But yeah, that is kind of a way we see of moving forward. This technique is kind of, if we're able to go into the field and ground truth one particular area and train the algorithm on that area, and then map a much larger part of the terrain, a much larger area. Yeah, how well does the classification work when you only have training data for one small fraction of it? So that's, yeah, future work.
Yeah. And Roy writes, between deployment and producing a classification map, how quickly can this be done? So he's envisioning a disaster scenario where a map like that would help with hazard mitigation or rescue operations.
Yeah. So the great thing with producing the thermal maps, at least, is because the thermal images are low resolution, they run through the photogrammetry really quickly. I think anyone listening that's used structure for motion in Agisoft on visual images is aware of it. Depending on how many, if you have 500 images or something in a model, it can take hours, overnight, days to run on a laptop. A thermal image, you can make a thermal map in minutes. And so you could create this heating rate map. You could do your 3 flights. You have to wait a certain amount of time for the surface to heat up through the solar input, but then you can crank it through Agisoft, and then I do the heating rate calculation in MATLAB. And so if you do, it's the thermal data, it's probably something you could do. You could do the flights in the morning and maybe have a map, certainly by the next morning, a heating rate map by the next morning, if not that evening. And then if you're cranking out, and then if you have a visual DEM, yeah, it's probably something that's looking at, you're looking at 24 hours at least to crank through, if not maybe 48 if you have a big area of visual images. And it also depends on your computing power. Little laptop, it'll take longer. So it's not the fastest thing in the world, but it's not, you don't have to like wait a week. It's not like, it would maybe be faster than, it could be faster than a satellite return.
Okay, that's great. I think you've covered the bases here. I think we should thank Brett again. Brett, what we usually find happens is that a few people stick around to the very end just to chat, kind of the equivalent of, the people that come down to the podium after the talk. So
yeah, certainly.
Mind sticking around for a second or two, but thanks again for a great talk. And everyone, please join us next week.
Yeah, thank you. Appreciate it.
And Brett, one thing that you also will have with a copy of this is all the comments. It records the comments as well, so you can see those later.
Oh, great! Yeah, that's that'll be awesome to have. Yeah, this is the first. This is the first time I've presented this in talk form. I had a conference poster a little while ago, but it's nice to actually talk about it for the first time and have some feedback.
Yeah, it's great. It's great to see all the work.
Yeah.
I got to go, but I want to thank you for giving a nice seminar and helping make our series a success.
Yeah, Ben, thank you very much for the invitation. It's good to see you again.
Yeah. Take care.
Yeah, thanks. You too.